everyone, welcome back. We hope you enjoyed a lunch, or if you're in a different time zone, maybe a snack or a stretch during the break. I'm Sydney Gladman. I'm MII's Chief Scientific Officer. We're going to start back up with our next panel session called Synthetics, a Succession Story. If you're a fan of the HBO show, we think this panel will be just as riveting. But instead of family business drama, our focus is on how we topple the Goliath that is the petrochemical-based fibers currently occupying over 60% of our textile material mix. We'll hear from three innovators offering next-gen alternatives to synthetics. All three use fermentation-based approaches where microorganisms like bacteria and yeast are used as factories to create different types of material solutions for the industry, from bioplastics to proteins. I'll be moderating this session. And first, I wanted to set the stage for the succession story, as we call it, on synthetics. How did we get where we are, and how do we move forward from here? So I'm going to start with a little history lesson. How did synthetics come to dominate the production of our material mix today? So the first man-made fiber, as those may know, to dominate the textile market was viscose, semi-synthetic, also known as rayon. And this debuted at about the turn of the 20th century. It was actually dubbed artificial silk. And this opened everyone's eyes to the role that novel fibers could play in the textile landscape, to offer alternatives to our historical animal and plant fiber incumbents. So as we know, viscose still occupies a decent share of our material mix today, but later DuPont, a historically influential chemical company then and now, was an early player trying to improve the process and properties of viscose in the 30s, spending in just 1 year $1 million, that's about $20 million of today's money, on viscose research, but really not getting that far on improving the material beyond its basic properties. So one day, one of DuPont's chemists convinced management to dedicate more time to pure scientific exploration, to innovate on new materials, instead of just trying to tune existing processes and materials. And they hired a Harvard academic to fill the role. As a result of this investment in innovation, around 1940, DuPont's nylon hit the scene with a public announcement at the World's Fair. And it was a raging success story. Almost immediately when the material was made available, there were literal riots of women wanting to get their hands on the latest nylon stockings. Now we call them nylons. This early success spurred more innovation. Over the next few decades, we had polyester, acrylic, and spandex following closely behind. It was an amazing time for the textile industry, uncovering incredibly versatile solutions, new products, applications, and performance. And then we kind of stopped innovating. The last innovation widely adopted by the industry was lyocell, invented in the 70s. So it's been, 50 plus years. We've been mostly just making more and more of the same stuff. So over this time period, the production of synthetics has continued to skyrocket. And we're slowly coming to realize that while these synthetic materials offer unparalleled efficiencies, unique properties and performance, and low price points, being these petrochemicals, they come at a detriment to the earth and its inhabitants, which I think we're all well aware of. We've heard a lot about this already at the conference so far. So I give this history lesson because I think we forget how our current material mix came to be dominated by synthetics. And in that history lesson, we should also see that our current material offering doesn't have to be permanent. Change was possible before, it's possible now. We can reverse the trends of increasing petrochemical production. There are positive things, actually, to learn from the adoption of synthetics, these years ago, not just the negatives in our current war on plastics. We can learn from the nylon origin story, where companies that still valued profits realized the power of investing in pure scientific exploration. We're completely able to transform the textile landscape. So somewhere along the way, we did forget how powerful this investment in pure science and research development, open-ended exploration, introducing new materials can be. But I think we can all see, at this conference, we're already seeing that innovation is returning to textiles. We don't have to be stuck with our current material offerings. As a material scientist and engineer, it's amazing to see material science come into the limelight. As a nerd, I love seeing it, in everyday talk these days, to see hundreds of innovators working towards a new material economy. But unlike our historical textile innovators in these synthetics, upon conception, they had no clue about the environmental and ethical challenge that would come to light in the future. But we know more than we knew then. We can now innovate with sustainability in mind. We can learn from our incumbent materials, engineer sustainability from the ground up, learn what used to make these materials tick, what were their pros and cons, and then look around us, see what's abundant, renewable, scalable. With some science and ingenuity, we can develop a whole suite of next-gen materials to disrupt both all of the petrochemical-based offerings, polyester, nylon, spandex, with smarter, environmentally preferable options. So who will be our successors to the petro giants? I think we have so many exciting innovators as a part of the next-gen materials revolution. So I want to introduce a few of them today. So let's start with DeLaine Mayer. If you could bring her to the stage. She's at Genecis.
Hi, I'm DeLaine Mayer. I'm the head of partner success at Genecis Bioindustries, and we are a Canadian-based climate tech and biotech company that converts mixed organic food and agricultural waste into PHA, or polyhydroxyalkanoate, which is a biodegradable, home compostable, and non-toxic alternative to oil-based plastics. I really appreciate, Sydney, that you started with the history lesson, just to give like a 30-second version of that for PHA. Genecis did not invent PHA. PHA is a naturally occurring process of bacterial fermentation, and PHA was actually discovered about 100 years ago in wastewater treatment facilities. But it wasn't until the 70s when researchers really started to explore PHA as a potential material that could be used for different production processes and materials across industry. But at that point, oil and gas was so deeply embedded in the global economy through, huge refinery the development of huge refineries and the expansion of oil and gas extraction in the 50s and 60s, that really low plastic prices were kind of locked into the economy. And so now that we have political will, consumer interest, brand interest in next-gen materials, PHA is hopefully going to start showing up on our shelves and in our clothing soon.
Yeah, so everyone remember that, the PHAs, because I think it's one of those new materials we're going to see a lot more of soon. Next, I'm going to add Martin to our stream. Hi, Martin.
Hello, everyone. I'm Martin. I'm sitting actually in Munich in the southern part of Germany. I'm representing AMSilk today, which is a company that does artificial silk, as you know it from like the spider or from also the mulberry worms. And my background is I'm a textile engineer, and I spent like 30 years almost in this industry. I've been with multiple outdoor brands and fashion brands. And when I started in this industry, that's also a little bit history, personal one, but I was a climber and a skier, and I was always very keen to influence materials for performance characteristics. So durability, waterproofness, breathability, lightweightness, and so on. I mean, that was like the old age, and now we can see really a trend, a shift towards more sustainable materials, but also not sacrificing too much of the performance. And at AMSilk, we have already quite a lot of interesting partnerships and really people acquiring us, which is overwhelming, to step into this new area of materials. And I'm happy to be here to have not just talking about performance like in the previous years, but also about smart performance and sustainability.
Thank you so much, Martin. And now I'm going to add Mike.
Hi, everybody. I'm Mike Saltzberg. I'm the CEO of CovationBio. Our company's 1 year old, but actually our business is more like 20 years old. We were spun out from DuPont. We were previously DuPont Biomaterials, and we spun out last June. We've been in the marketplace commercially now for about 17 years. Our flagship product for the textile industry is called Sorona. Sorona is a high-performance polymer. It's made partially from a monomer called BioPDO. BioPDO is, as Sydney mentioned earlier, made by fermentation from corn sugar. And Sorona brings some really unique softness and stretch and other properties to textiles and to carpets and other similar applications. So again, our company's been focused, our business has always been focused on bio-based materials and high-performance bio-based materials. And also, I think what maybe I can bring to this discussion is we've been at scale now for a while. We're about a $250 million company. We've been at scale now for 15 or 16 years. So we've seen a little bit about the beginning part of this process, bringing new technology to market, but also the challenges in making things get to scale and bring them at a reasonable price point. So very excited to be part of this discussion. I think Sydney's exactly right. that the time is now to really look at some of these innovative things. And what DeLaine said earlier about the world's perceptions is changing in terms of willingness to pay and willingness to entertain new ideas. So I think it's really a great time. I personally come to this as a scientist. I'm also a PhD material science person and come from that kind of a perspective, and have learned over the last 16 years that I've been leading this business a little bit about the sustainability end of it. I'm very pleased to talk about both. Thanks, Sydney.
Thank you so much. Yes, and thank you to all three. I think, each of these three different materials, although made with some similarities in your process, offer different solutions for the textile industry. So it's going to be really, really great. One of you guys, I think, still has the stage open, and I hear an echo. So just make sure you close out if you have another tab open, because I'm not sure if anybody else can hear that, but there's an echo. Okay, so I'm going to start with a question for Martin specifically, because it kind of, from what I was just talking about, this history lesson, right? The origin of a lot of these synthetics were to be alternatives to animal materials. So viscose, nylon, polyester were alternatives to silk. And now we might be able to use silk to be an alternative to polyester and nylon, right? So it's kind of an interesting coming full circle. And I wanted to see your perspective. How can we use other material categories like proteins, right, to kind of fit into this alternative to synthetics space?
Yeah, so let's start with biofabrication, because it's rather new, and there is a ton of companies out there in the scale-up phase, in the startup phase, and I think we are learning our lessons right now. So at the moment, I think it would be it's very hard to challenge at this point of time polyamide and polyester with fermentation processes, for the simple reason of costs, because the polyester polyamide industry is huge, is humongous. I mean, it's great, big time, and we are starting with small, fermentation batches that are still big for us, in the biofabrication world, but there's no way right now to compete price-wise. But I don't see on the long run absolutely potential to indirectly substitute fibers that are, fossil fuel based. And we are at the very beginning. And silk was also one of those, really holy grails to copy and to mimic. And viscose was done, and then there was polyester polyamide. But the original product is still a protein-based fiber. And that's a super complex, polymer and amino acids. And life is made from amino acids. That's the building blocks we are all made from. So we are very, very optimistic and energized that silk is only the starting point. So we have right now customers that are looking especially to substitute their mulberry silk with our products, because they are chemically and physically very congruent. So they behave and they feel and they behave in the weaving and knitting mills as silk. But our monomer, like the product we are making our fibers out of it, the silk protein is a humongously huge, complex amino acid chain with more than 1,000 amino acids in a row. So there is numerous, opportunities to change this amino acid sequence. Mm-hmm. And we can go, as any spider has different silks, we can go hydrophilic, hydrophobic, we can go elastic, we can be stiff. So everything is about to be changed. And there's a huge vector going into this direction. And over the time, when also the fermentation capacities will go up and the fossil fuel costs will go also up, there might be a break-even well. Will be really interesting to substitute also parts of the poly business with fermented proteins. If you want to ask before timescale, I think that's maybe interesting for the audience. We believe within the next 5 5 years, we should be in a position to venture into the performance characteristics of polyester polyamide. And then, let's say in 10, 15 years, there will be a significant chunk will be not fossil fuel based anymore.
Thank you for giving us that timeline too, because I think you've got to set kind of the realistic expectations here, right? That we're not going to come and be able to disrupt the whole industry overnight. That it will take time to develop these materials and have them infiltrate the market.
But as you started in the beginning, viscose was also it took several decades to make it ready for market, and same for polyamides.
That's absolutely true.
So it's not an easy one.
Absolutely. Yeah. So we should all take that with a grain of salt here. So I have a question that's a little bit more general. I think any of our members here can answer, and it actually builds upon an audience question that just came in as well. And it's on fermentation, right? So we're talking about fermentation. What is fermentation, right? It's you take some sort of carbon-rich feedstock typically, and you put it in a bioreactor with some engineered microbes, whether those are bacteria or yeast, and it outputs, something that you're desiring, right? So you've engineered that organism to make something. So that's just the general principle, right? But everybody has their unique kind of way of doing this. One of the, things that come up a lot, Mike, you mentioned corn being an input, corn sugar has been input into the Sorona process. There's been concern about feedstock, right? These materials that we're putting in, if these are food products that we're relying on, is there going to be issues with food scarcity, land use changes, because we have to grow a lot more corn, right, to supply all of the bioplastics we might want to manufacture, more pesticide use, et cetera, et cetera. So I wondered, you guys, I'm sure, have had your questions as well. How do you approach, this question as it comes up about feedstock? And I'll have Mike start, just because you're just talking about Sorona, and then DeLaine, I'd love to hear from you as well.
Okay, sure. Yeah. So I think the question that, as we typically experience, it comes in a couple different ways. So one way is, hey, you guys are using food. Is that an ethical thing to do? You're taking food out of people's mouths to make this whatever product you're making. And the reality is, for example, in our case, what we use is dextrose that comes from cornstarch. And the corn that cornstarch comes from is what they call industrial dent corn. So it's not the sweet corn that you go to the farmer's market and buy and put on your barbecue. It's basically an industrial crop that today is used primarily to feed animals. And the other big use for corn today, at least in the United States, besides making high fructose corn syrup, is to make ethanol. So today we've already made a choice where about 1/3 of the corn crop goes to make ethanol. So when you say, oh, well, your bio-PDO process that uses corn sugar, is that, are you utilizing starch that would have been used for food? And the answer is no. It's really, today a lot of it's used in ethanol. I think the bigger question is about land use. So a lot of times people ask the question, aren't you using land to produce this feedstock that you put into your fermentation process? Isn't that taking land away from food? Well, let's be clear, that choice has already been made. People use land to grow cotton. Cotton is not food. We made a choice a long time ago to cotton. By the way, cotton uses a huge amount of water and a huge amount of fertilizer. It's a much less efficient crop, for example, than corn is. You can get a lot more value and a lot more output from an acre of corn than you can from an acre of cotton. So that's one aspect of it. And I guess the final piece I would say is, when we talk about particularly the use of corn, it isn't a question of are you using this for food or for materials. It's for both. The corn that comes into the corn factory is split into different streams. Most of that corn still goes to feed animals, which feed people. Only the starch fraction is utilized typically in these industrial fermentation processes. And again, that starch would have been used for industrial starch or high fructose corn syrup or ethanol primarily. High fructose corn syrup, people are using less of it for health reasons and taste reasons. Ethanol, as people drive less and we go more towards electric vehicles, there's less demand for ethanol. So there's a need to find a use for this starch in order to create all the rest of the fractions that get used to feed animals. So that's sort of a long answer to the question. We've been talking about this for a long time. Frankly, I think most people have kind of gotten to the point where they understand it isn't a question of or, it's a question of and. Thanks.
Yeah, I'm happy to jump in on that too with maybe a different perspective from Genecis. Within the US, 40% of agricultural or 40% of food that is grown for consumption. Sorry, I'm echoing also. Is that heard from everyone?
Yeah, could the other speakers mute? And let's just make sure we're all individually speaking. It might help because I think somebody's got a background going there. All right. Yeah. Cool. Mike, I think it's on your end just as a troubleshoot in the meantime. Thanks.
All good. We'll figure out technology one of these days. But yeah, so Genecis takes a little bit of a different perspective to the feedstock question, in part because food streams are a commodity, not just for human consumption, but whether they're going for, ethanol production, as Mike mentioned, for animal feed, all of those are actually paid streams for food waste as a commodity. To be used elsewhere in the industrial economy. And so Genecis takes the perspective that the cheapest way to produce PHA or bioplastics is actually through food waste. And within the US, 40% of food that is grown for human consumption actually is wasted. So when you think about the water, land, carbon, transportation footprint associated with all of those waste products, and for that to just end up in the landfill where it contributes to methane and carbon emissions, not only is that a huge environmental deficiency, it's also economically inefficient. And so Genecis is scaling our technology with mixed organic food and agricultural waste as our feedstock because of this dynamic within the food market. And so by using mixed waste, we're also able to produce PHA that is at scale going to be some of the more sustainable bioplastic and biomaterial options available. As Sydney mentioned, we are using microorganisms that are tuned to process mixed waste, which can also be, it's one of the reasons why companies have not used mixed waste in the past. It's really hard to de-risk. The technology development timelines are much longer than using homogeneous feedstocks that are sugar or starch based. And so there are technology hurdles to overcome. But, just speaking on Genecis and where we're at in terms of developing that tech, we're scaling up a demonstration facility with Stormfisher, who is the largest Canadian biogas player. And the idea really is to see if we can generate consistent volatile fatty acids, which is a precursor to PHA production, and confirm that we can do consistent VFA production from mixed food waste, which will ultimately get us consistent PHA yields for use for biomaterials development across a variety of industries. So that's how we're thinking about feedstock.
Thanks so much. I think there's so many factors to consider and it's very complex, right? So I think that there's what you can do now versus where you want to go, right? And that's always, we're probably going to be constantly evolving on, I think, this feedstock issue as we move forward. Martin, if you had anything to add in, please jump in. But otherwise, I was going to, kind of go to a different question. But did you have anything to add on the fermentation feedstock front?
Very quick one. One. We are in the middle of in between. So we are using right now cornstarch for our current fermentation processes, which are to be scaled up. But we have a lot of customers asking about our feedstock, and we are, in terms of the answers, are in between DeLaine's and Mike's answers. So I think the customers are very sensitive on feedstock. So we need to give an answer, and we need to look for second or third generation feedstock carbon sources that are not, food related or, agricultural related anyhow. But I always ask my customers, well, if you are so interested in our feedstock, have you ever asked the same question on the fossil fuel-based fibers? It's somehow a little bit interesting. But I'm with DeLaine. I think we can work out even a better way than using just cornstarch.
Just to add to that, right? Like the perfect cannot be the enemy of the good. Like materials transition is going to have a number of stepping stones in the same way that an energy transition to cleaner fuels is too. So yeah, I very much second the spirit of that sentiment from Martin.
Thank you so much, guys. So, you just brought something up, Martin, that I kind of want to, turn over to another end. We've been talking about beginning of life, how you're making your materials, but how are we actually getting them to, you know, your customers and then the consumers. And a question that's come up a lot is, right, how do you balance the demand right now? There's a demand for high volumes of these new materials when you're still at low volume production capacity. And Martin, I didn't know if you would have something to share on kind of that thought there.
Sure. Maybe I gonna start with sizing the demand, or sizing right now our capacities. In the current year, our fermentation capacities is within a 10-ton scale per year, and we add a single digit every year. So next year we're gonna focus on 100 tons of protein and then 1,000 tons, and so on. So we have only 10 tons, which is in the textile industry like nothing. And we have to be really careful and, you know, selective with what we're going to do with it. Since the Adidas launch and the demonstration of the first like upper made from our artificial silk, that was 2015. We have like numerous of hundreds of inquiries and customers asking for samples, prices, technical data sheet, and so on. And from that list, as we cannot sample and work with all these customers and, you know, material scouts and design offices, we pre-select, first of all, is there a good brand and product match? And is the customer and the brand, you know, willing to commit and to work with us? Because they, as also we, are going into a little adventure. So we don't know what we don't know at the moment. So there will be surprises along the way. And it needs patience and also time and commitment. So if a customer asks, hey, can I sample this for summer 2024 or winter 24-25, then the story is almost over, because it takes a little longer, you know, to see how everything works together. And the way we work is we have like 3 different opportunities or options. The majority, what we have is preferred partnerships. That means our brands are, you know, committing with us on a project, on a product form, and we're mapping out a project, you know, time scale and the map and milestones, and it's also connected to a certain, you know, R&D investment from the brand. So if we reach those milestones together, then we continue and go for the next step. The preferred partnership is something with a timeline between 1 and 2 years to have a feasible and also then fit for use product that is ready for market. We have another model, which is what we called strategic partnership, and that's a little longer from the horizon. So we are venturing with our brand partners and JDA partners into not just derivative fibers and filament types from the same protein. We are going into the protein design. So we really change the characteristics of the protein to what is needed. That's a time frame of, let's say, 2 to 5 years. And we have another one which we call just partnership, which is like the easiest stepping stone or like lowest hurdle. Where we have partners like Omega, for example, who are just buying ready developed pieces from us, but in small quantities.
Thank you. That was really descriptive, like all the different ways that you're approaching kind of the different partnerships. I think that's really unique, right? You know, we have to think of these new materials in new ways and have kind of versatile strategies, right, to work with these different brands. You know, I think something we've actually noticed at MII, we have a report that we put out on kind of collecting all the brand partnerships, mostly in kind of the fashion, automotive, home goods industries. And we see that, right, there is that variety. There's people that co-developed, that invested, that, you know, worked on the R&D together. And then we've got people that are doing a little bit more off the shelf, let's say, right, purchasing as well. But, you know, we have to rethink, you know, kind of how we work together in this space. And on that note, I wanted to actually go over to Mike on the same topic, right? You guys are farther along in the journey, you're at commercial scale, but in your early days, right, how did you approach, you know, getting customers' demands with low supply?
Yeah, so I think one of the most important things to talk about here is the need to do application development. So one of the issues that's really difficult in the textile industry is how many steps there are between a material supplier and a garment that somebody can buy at a retailer. So if you want to bring a new material to the market, you have to ensure that it spins well into a fiber and that can be woven or knit, and that it can be dyed, it can be cut, it can be all the things that have to happen between you as a material supplier and the brand. And if something fails at any one of those steps, in those very many steps, your material will never reach the market. So I think that's one very important thing. So one of the things that we did was years before we actually built our commercial plant, we started working with a couple of very key partners to do the application development so that when the plant came online, we had what we called a killer app. So the classic Sirona story that a lot of people in this industry know about is we had a long-standing partnership with Mohawk Industries to make carpet out of Sirona. And so roughly, half of our first plant was sold out to them before we actually started the plant up. And it took a couple of years to ramp up the volume, but that was really critical. And so I think when I talk to people that are starting new materials companies, I would say two things. One is that sometimes they underestimate the challenge of what's downstream of them. They're sort of saying, hey, I did my job. I invented this really great material. Look at its fantastic properties. But as I said to you, Sidney, nobody cares about your material. Only you really care about your material. And so if you don't make it work for every single step of the chain, for the fiber spinner, for the weaver, for the dyer, for every single person in that chain, all the way to the retailer, if they don't find a way that their business is better because they're using your material will fail. And so that makes it extra daunting because it's already hard to invent a new fermentation process to make PDO or silk or PHAs. It's already really, really hard to do. And that's just the very beginning of the process to get your material actually to market. So I guess that's the main thing. So one of the things that we did is what we call these killer apps. We had a couple of different applications of Sirona in carpet, and then in apparel, we have a particular fiber configuration called bicomponent stretch that we took out to the market, and that helped us fill our plants up so that we could survive the valley of death.
Really great lessons, I think, for any innovator, right? Not just people in fermentation, but I think any next-gen innovator should learn, like, you've got to map out that entire application, process and how the supply chain is going to use your material. I wanted to, we just talked about you're a little bit more mature along the path at Sirona. DeLaine, you're a little bit earlier in the process, right? PHAs are also, as a material new, but also the company is newer, having founded in 2016. And you guys have lots of different potential verticals that PHA can go, right? This is a raw resin, a plastic, right, feedstock that can go in packaging and, medical devices. It could be in a lot of places. When we talk specifically about textiles, right, what unique challenges are you facing, right, in getting PHAs into textiles?
Yeah, this really tags on to what Mike was saying about it's not just working with the end brands that want the material, but it's the compounders and converters in the entire plastic supply chain, and finding partners really at every node of the manufacturing process that are willing to test and potentially scale a new material. So one example, if a brand comes to us and they're looking for a fully biodegradable PHA-based widget, but the current converter that they are locked into an agreement with is totally unwilling to work with an emerging material, like that's a no-go in terms of qualification, to what Martin was saying. And so, when it comes to textiles, it is a longer R&D horizon for single and multi-filament fibers. Genecis has done some work in terms of PHA blending with other biopolymers, but it's more challenging than other applications. And so we have really defined internally what our product roadmap is, like what are the applications that we want to go after first, and therefore the brands that might be the best supporters earlier on in our development, again, because of those volume limitations it's not an issue necessarily with scalability, but it's like, what's at scale today? And brands want these new materials yesterday, but they also want them completely vetted with all of the certifications that prove that the data makes them better materials than the incumbent product, et cetera. So yeah, that product road mapping exercise for us was really crucial in helping to develop the standard for the partnerships that we want to target. And I really love Martin's language of the preferred, the strategic, just the baseline, like direct to purchase order partnership. So that's absolutely the playbook here.
That's good. I mean, it's good to learn that it seems like it's working, right? Multiple people trying the same thing, and it seems like it's working. So we actually had a question from the audience I didn't think we had answered yet. It's from Kevin Ward. Has anyone identified sugar suppliers for their fermentation-derived materials that actually disclose or differentiate based on their like carbon and water footprints, land use, sort of their environmental impact? I can put my answer out there. I haven't seen this, so I want to see if any of you guys have seen it as well. It actually sounds like an amazing business opportunity for someone to do this research and make it sort of like a pay for platform for people to get this information. I'd say right now you probably have to go to the individual source, right, and then go through whatever information they may have on an LCA or other research that they've conducted. But I doubt that there's just kind of like a library of this, for people to use. So does anybody else have any comments on that?
Yeah, I'd love to talk about this one because we have some recent news about this. So our joint venture to make BioPDO, where we do the fermentation process, is with a company called Primient that used to be known as Tate & Lyle, used to be known as A.E. Staley. They're one of the big corn processing companies in the United States, along with ADM and Cargill. And what we've done with those guys, first of all, is that from the very beginning of this process, we were committed to making sure that we were 100% transparent about the environmental footprint of what we're doing. So there's a refereed, completely, a very in-depth LCA. It was, refereed by outside folks. That's been published. You put out a sustainability report. I encourage you to go to our website, pull down the sustainability report. It'll tell you all about it. And the next level of this is it's not just enough to say, hey, I'm using corn and corn is a fantastically efficient crop. It's also how was that corn grown? And so what we just announced actually a few weeks ago that along with Primient, we've joined a program called TrueTerra. TrueTerra is a regenerative agriculture program that works with farmers through the Land O'Lakes Farmers Cooperative. It works with farmers to ensure they're using regenerative agriculture practices. So in other words, the corn is grown the right way to minimize the environmental footprint of the growth, but also to make sure soil health is there, that there's a minimal amount of chemical inputs. All that stuff is done. And so we think it's incumbent on us as material suppliers to not just say, hey, we used fermentation, isn't that great? Or, hey, this was made from corn, isn't that great? We have to give people the information so they can see what is the environmental footprint of your product down to, greenhouse gas emissions, all that stuff. And then also, can you guarantee me that this corn was grown in an environmentally sustainable way? The answer is yes. We're part of this program that certifies it. So I think it's a great question. I think that's where we're headed. I don't think it's going to be enough to tell people, hey, trust me. We don't subscribe to that. We think you've got to give people data and you've got to be really transparent. So that at CovationBio, that's kind of our whole approach. And so I encourage you, go to our website, look at the sustainability report. There's a lot of information there.
Awesome. Martin or DeLaine, if you have anything else to add on that front, feel free. Otherwise, we can go to another question.
Just to add to the spirit of that, right? Like one pillar of manufacturing or materials, the development and growth of that part of the economy incentivizes the development of all of these other ancillary technologies that are more sustainable. And so I really love that story of like bringing in together what a circular economy or just a sustainable economy can look like, because the success of, a sustainable material can trickle down to so many other industries that touch that: transportation, ag, et cetera. So just wanted to call that out.
Awesome. Well, I think, there's a lot more to do, but it's great that I think that we have people really thinking about this, right? That, from the ground up, you're able to know that this is important and bring it a part of your journey rather than to go back, right? Which is what incumbent materials are having to do right now. Try to go back through their convoluted supply chains and figure out what the mess is. I think it's a lot easier to just start right now. So really commend you guys. So we've been talking a lot about beginning of life, how materials are made, environmental footprint, a lot of these things. I want to talk about another topic, right? There's a separate topic on the sustainability front, which is end of life, right? So often these things get completely like convoluted and people just kind of say them all in the same way. They're two different things to think about, right? I think as material producers, you guys have a lot of control over beginning of life, right? You know, like where your material is coming from. You're able to measure it a little bit more effectively. With end of life concerns like, microplastic shedding or pollution, right? Are you recycling? All of these things. It's a little harder for a material producer to control and to make sure that, you can fit into some, let's say, circular or, better future. So I wonder, if anybody has any thoughts here on how do we now think more about end of life, even though it is harder for you to actually have control on as the producer. DeLaine, maybe you want to start on this one?
Yeah, absolutely. If you look at statistics on recycling, they point to a pretty ineffective system, regardless of your stance on recycling. Like 4% of materials that could be recycled actually make it into a recycling stream and valorized into a new product. So again, that's just not efficient. You can throw trillions of dollars to triple the impact of that system and suddenly 12%. So we have to really design products with end of life in mind, with the assumption, and it's unfortunate, but with the assumption that our products are going to end up in the ocean or rivers and waterways or the landfill. And I think when you start designing materials with that reality at the forefront, instead of there's a little bit of delusion, I think, about upcycling programs and where products actually go. And there are some more closed loop, smaller systems that do work. But in general, a lot of my waste is going to go to the landfill when I'm done with it. And so if I design materials with that reality in mind, can I change the framing of the entire system? And so that's why we're making PHA with food waste, again, a more sustainable feedstock on the front end, but PHA itself is totally marine biodegradable, non-toxic. There is no, microplastic shedding because it's not a synthetic plastic. And so that for us is the big motivator for scaling PHA. It's with reality in mind. It's with end of life in mind.
Thanks so much. I wondered, Mike, I know you might have different philosophy, having seen kind of the whole plastics industry and trying to break into that space. What are your thoughts there on end of life?
Yeah. So first of all, I wanted to, strongly agree with what you talked about. I think we're having these circular economy discussions. It is really difficult when people are talking about the beginning and the end, and they really are completely different. So as a material supplier, the biggest influence we can have for the positive is we're the gatekeepers of what gets into the circle in the first place, right? We're the ones that are taking these feedstocks, whether they're petroleum based or corn or algae or whatever they may be. We're the ones that are gating those choices. So frankly, the group that's on the call right now, that's where we can do the most good, is by making sure that we're not, part of this addiction we all have to fossil fuels, that we're bringing different solutions that can bring high performance materials that utilize things that are renewable. So I think, first of all, that's our main thing. But for us, the issue as material suppliers, and DeLaine touched on this, is what holds back more recycling is typically two things. One is the design of the products, which we don't control. It's controlled by the OEMs. And also, obviously, what gets done in different municipalities in terms of how they manage their waste, right? So that's the first thing. So as a material supplier, I'm frankly mainly focused on two things. One is using as much renewable, sustainable feedstock as I can to gate what gets into the circle. And then secondly, what I call do no harm. In other words, we have to make sure that whatever we make is either biodegradable or recyclable or both. We can't be contributing to, things that have no chance of ever being used again. But it is very difficult as a material supplier to be the one that makes that choice. The other thing I would say is, and this is maybe a little bit on the cynical side, but a lot of the people that are banging the drum about recyclability are companies that have huge investments in petro-based plastics, and they're trying to justify the fact that they want to keep doing their business. And the way you know that is that every year more and more and more PET and polyethylene and et cetera plants get built. So if they really meant, we're going to start really, really recycling a lot of stuff, they wouldn't be building new plants. So that's part of the issue too, is we have to be real about what we're talking about. I think, frankly, the best solution to the waste problem is to use less stuff in the first place. And so in the textile world, what that means is fast fashion has to go away. People have to buy one T-shirt every few years instead of 10 T-shirts every month that they throw away. And we as material suppliers can help with that, because if we can bring out higher performance materials that last longer, that survive more laundry cycles, all that, and we can work with designers to make more fashionable garments that people are happy to keep for 10 years, we can greatly reduce the waste problem. for me, that's the main focus we at CovationBio have, is the things I talked about, doing no harm, using bio-based feedstocks, and then doing everything we can to create higher performance so that these garments last longer. I think that's really the answer. I mean, there's a big debate about is biodegradable a good thing or a bad thing? Because basically, if we go to biodegradability, we're taking materials back to their original CO2 and water. That's what it is. Well, you can do the same thing by collecting it and incinerating it, and then you get the energy value back. And so there's a big debate that happens on which one of those is better for the environment. So, I, as a citizen, I care a lot about that. As the CEO of a biomaterials company, I focused on the three things I mentioned. Thanks.
Yeah, and I think it's a great point, right? I think there are different end-of-life strategies that will make sense for different products with different expected end use, life cycles. All of this is going to matter, right? So I like the do no harm approach, right? Try to fit into something, that's going to not make for worse problems. But I do think as we continue to evolve and think through what the circular strategy should be, it's not a one-fits-all solution, right? We probably should not just make everything biodegradable. Some things maybe should be biodegradable. Some maybe we want to make more, circular, recyclable. There's probably a lot of approaches we need to do, and we need to do it very thoughtfully, right? So I think that's, great to hear. And also your note on performance. I think we've said this a lot during this conference. I think every panel has brought this up, that we can't sacrifice performance. We actually have to bring new performance in order for next gen materials to be adopted. And it's not just about sustainability. So I'm really glad that we're continuing to hear that theme again. Martin, did you have anything to add on that front?
Sure, if I have a minute. So we have at AMSilk a couple strategies, because that's really depending on the market you are in. In Europe, for example, it's not allowed to put any apparel on the landfill. It's forbidden. So what happens is, because it's not allowed, we are exporting fast fashion like shiploads to South America, to Chile, to the Atacama Desert, and they just for a certain amount of money they are throwing the stuff in the desert, and it's completely crazy. And this is a super dirty industry. Our products are fully biodegradable in soil, but also marine conditions, and it's very easy. So every spider is eating its own net and is recycling it. So it's amino acids, like our meat is made, our skin is made from. So it's a natural product, and I believe a lot in natural products. So a sheep has hair, and if you cut off the hair, it's a fertilizer for the next round of grass to grow on. So I believe strongly in bio degradability, but that's not applicable for Europe, for example, by law. So for US, that works great. In Europe, we have to recycle it. And so we can put our fibers or garments or whatever is made from our stuff back into the feedstock to feed our bacteria, or we can put it into a solvent when it is, clean and chemically, fair enough, so it's not polluted by any other stuff. And that might takes me to another point. The fiber is one thing, but what we add to it along the value chain, dye stuff, lubrication, all kinds of other, textile, treatments, that might also be a challenge to disrupt or make the recycling very complicated, but also the biodegradability.
So it's a really great point. That's actually the next question I wanted to ask, which is related to the rest of formulations in the finished products, right? So we're all, everyone here is trying to make the base sort of substrate fiber, but there's always going to be more, that kind of gets added on: dyes, flame retardants, PFAS, which is, we all know, really, really terrible. All these things that we need to worry about. So how do you guys, as those fiber suppliers, kind of look to the end of the chain and try to prevent, let's say, problematic additives in your formulation? Do you have control? What needs to be done so that you can, we can all get to more holistically sustainable products and not just the base fibers? Martin, you were just speaking, so I'll let you keep going.
Maybe I can keep this, a little bit short. So we started with our fiber with Adidas. It was undyed. It was completely free of any dye stuff, and the color was the pure reflection of the light that gave this kind of light, gold or champagne color. And that was great, and people loved it. And there's lots of trends right now to have undyed products in the market, shoes and apparel and whatnot. But we have also customers. We have one prominent car manufacturer that is working with us on a partnership level, and they have shown cars on a show car level, and they want to have color matching trims and the car and the whole design language. And then the whole thing starts. It's automotive industry, so there's a certain threshold of light fastness, wash fastness, fastness to sweat to whatnot, and you have to always tick the box on the very top end. And we started to dye with metal complex dye stuffs. That works. It's great. It delivers great performance, are an array of colors, but we are losing the biodegradability. So it's something we also have to work with our customers to. It's a learning process, and I think it takes a little time. So we work, for example, with a Swiss dye stuff company on biodegradable dye stuffs with a good also performance characteristics. So there might be solutions. What we will not have is like the full Pantone book of colors and every color is working perfectly. There might be a limitation at the beginning. But just think of indigo. Indigo is like a natural dye stuff that was used for wool in the beginning. Now it's used for denim. That works great for for protein fibers, and it's biodegradable. So here we go.
Yeah, we can learn a lot from our past, right? Before we had these synthetics, right? Can't we look back to nature for solutions? I think that's a really good point. DeLaine or Mike, anything to add on that topic?
Yeah, I wanted to bring back the comment on not compromising on our technical and performance requirements, which I think is really interesting in the plastic space when we think about over-engineering, given most products have a planned obsolescence. So a lot of materials have requirements that allow them to long outlast when the product is actually designed to stop working. We see this a lot in electronics, but it's true for most of the applications and the components within our home and within the textile and fashion space as well. So, the conversation I think can be geared towards how to engage with clients in a really honest way that it truly incorporates how they view products end of life. We hear a lot of companies that say like, well, this is designed, it has to meet the requirements to function in someone's home for 20 years. But we know that most of their, through their marketing data, through their sales efforts, that customers are throwing things out after 2 years. So why are we designing for 20? Because that impacts the dyes, the additives, all of these other materials that have to be combined with the base resin that maybe then loses, to Martin's point, loses the biodegradation or even industrial compostability qualifications because now it's been blended with so many other things. The one maybe caveat that I would say to that is still having a base resin that is biodegradable, but maybe has been made less pure in its mission by blending with synthetic additives, for example, is that material was still not produced from petrochemicals. And there is still a value in that when we look at the entire LCA and the data collection for that product. And I'll give the example too of, Cancer Alley in Louisiana that houses 80 miles worth of petrochemical refineries and plants and has the highest cancer rate in the United States and is mostly lower and middle income Black and brown communities. There is a real cost to the way that we produce certain petro-based materials. And when we incorporate that even into this end of life discussion of, well, we've kind of ruined the biodegradation of something, if I have to pick, and I'll speak for myself as an individual, not as a representative of Genecis, if I have to pick, I'm going to have the PHA blended product that's mixed with the synthetic additive instead of something that is wholly synthetic. Again, it goes back to, are there milestones and stepping stones that can ultimately get us scaling this kind of technology faster? And there might be some uncomfortable gray area, on that road.
Yeah, I think that's fantastic stuff, and I really appreciate the perspective about balancing, how long is the product going to last versus how long does the material last. I would say also the other way to look at it is sometimes the products are designed in such a way that, for example, fashionability on purpose, designers put things out there. And, I have 2 daughters, and every year, this year, the jeans are narrow. The next year, the jeans are high-waisted, then they're low-waisted. They're doing it on purpose to make you buy more clothes. So that's something that I think we can change. And again, as material suppliers, the part that we can play in that is by keeping those garments looking good longer. I'll give you a very concrete example. So everybody wants stretch in garments now, right? And so primarily that comes from spandex, and spandex has a lot of issues, both in the way it's made, but also like you put 3% spandex into a garment, now it's not recyclable. So there's another way to get stretch, which is if you spin a fiber that's partly Sorona and partly PET, it makes a fiber that crimps up on itself. It makes like a little spring. And because it's a spring, the stretch and recovery last much, much longer than spandex does, because spandex is more like a rubber band. So you think about a rubber band, you stretch it enough times, it loses its stretch. So just again, making that substitution, not only are you replacing spandex, which is the way it's made isn't so great, but you're also putting in a solution for a fabric. Now it started with a material that became a fiber, that became a fabric, that became a garment, but that yoga pant will hold its stretch much longer. And so Lululemon buys our Sorona bicomponent fiber. They talk a little bit about the bio part of it, but they talk a lot about the fact that these yoga pants won't lose their stretch. I think that's something as material suppliers we need to work on. A second concrete example, it goes a little bit to what Martin was talking about, is what the material fundamentally is affects how it has to be treated downstream. So as an example, if you want to dye nylon, you have to use high pressure dyeing, lots of energy. If you want to dye Sorona or frankly other polyesters, it can be done at room temperature in a much simpler process. So again, in addition to thinking, because DeLaine's exactly right, the very choice you make about is this bio-based or not, I think that's the fundamental first choice, what gets into the circular economy. But then as material suppliers, if we can also be thinking about how is this going to be treated maybe 1, 2, 3 steps downstream, and what can we build into our material to make all those processes more environmentally friendly, that's also really helpful.
Awesome points all around. I've heard, basically, if I could summarize a lot of what I've heard and what we've heard throughout the conference, and one of MII's sort of guiding principles is progress towards perfection, right? We have to realize that there's sometimes going to still be petrochemicals, heavy metals, these other things in the mix right now until we get to solutions moving forward that can get them out. But right now, having taken out that base, right, petrochemical based material and replacing it with something new and more sustainable is a great step in the right direction. So it's good to keep in mind. Another thing is I was actually born in Cancer Alley. So that really spoke to me, DeLaine. I got out of there quickly. I'm okay. But it's really important that we think of the environmental cost, right, is more, something we haven't really incorporated into our thought of these materials. And that's the final question I want to ask, which is cost. Polyester, right, is about $1 a kilogram. Everyone knows it. It's super, inexpensive. How do we compete? How do we disrupt? What needs to be done to get to a point where we get these materials into the market and people stop buying, polyester? So anybody go from there on that topic? We got just a couple minutes to go, so please be brief.
I'm trying to be quick here. So our first commercial product was a watch band from Omega, and Omega is a famous Swiss watch brand. And just the bracelet from AMSilk fibers was retailed for $350, and there's 70 grams of AMSilk fiber included. So the ratio between amount of fibers and value of the product is easy to introduce a novelty fiber that is not $1 per kilogram. The next level we're going to do is we work with companies from Paris and from Italy, like luxury fashion brands. I mean, not talking commodity products, t-shirts for $6, $7, or $10. We're talking about really high positioned apparel pieces, small volume, high price, high value, but also making awareness of a change. And over the time, we're gonna go down with the price and go up with the volume, of course. And that's how the markets are working. To just think, hey, we can compete with $1 per kilogram right now, that's an illusion. That will not work.
Thank you so much. Anybody else? DeLaine?
I'd love to go at this one. I have two, really, I'm very passionate about this particular one because we've been around a long time, and this is what's holding us back from getting. We're 100 kilotons in scale maybe today. why aren't we much bigger? It's because of this exact issue about relative cost. So there's two things. One is a very small change in the cost of material at the beginning of this long process to make a garment results in a huge cost up. And that's a value chain problem. That's not a technology problem. So the example I always use is if you take a cotton t-shirt, 75% cotton, 25% stretch fiber, and that stretch fiber is either made from Sorona, 50/50, or all petro-based products, 5 cents extra material to put the Sorona fiber in there. The t-shirt that's made with Sorona sells for $14 more at the end than the one that's made with all petro-based products. So 75% cotton, 25% Sorona stretch fiber is $14 more than 75% cotton, 25% petro-based. That's not a technology problem. That's everybody in the value chain overestimating the amount of risk they're taking and trying to make extra super big margins as they go along, because there's only so many omega, risk bracelets. So if we're trying to make a really big impact, we've got to be able to get into that market. Number one. Number two answer is, we talked about Cancer Alley. The impact that these guys who are pumping fossil fuels out of the ground and turning into materials and proliferating them out in the world, they don't pay for all of those consequences. Today, they do not pay. And so the real answer to this to me is petro-based plastics are way too cheap. And they're way too cheap, not because these guys are super efficient, which they are, and not because they're at scale, which they are, but because there's no accounting for the damage that is caused by the choices we make to be addicted to fossil fuels. So that has to change. EU is ahead of everybody else. They're moving towards this, but there's got to be an accounting. And when that happens, when bio-based materials can be on not quite an even playing field, because we're still way smaller and they're still 100 years ahead of us in terms of getting down the price value curve, but a bit more of a level playing field where they're paying for the consequences they cause. Oh, and by the way, most governments subsidize oil exploration because it's a national security concern. So it's not only do these guys, not pay for their consequences, they get subsidies that we all pay for as citizens. So the other part of this has to be policy. And I've been competing in this market for 16 years with no help from anybody. We'll keep doing it. But to answer your question, if you want an acceleration in how fast bio-based materials are adopted, those are the two things. One, policy. Two, the value chain's got to cooperate in a whole different way and stop stacking margins so that the amount of margin that goes into a bio-based garment is 10 times more than a petro-based garment. Those are my two answers.
That was said wonderfully. I really, think that was a great call to action for everyone here. And we're a little bit over, so I do have to stop. I'm sure we could have kept talking about this topic forever because it's super, super interesting. So I want to thank you to our panelists here, DeLaine, Mike, Martin, for joining us. Feel free to, message them through the chat feature or the private message if you want to get more questions with them. But we're going to move on to our next session now. So I'm just going to take everybody out real quick. Bye, everyone.